Welcome to the video on separable differential equations. This is day one video, and in this video we're going to focus on how to solve for the general and particular solutions to separable differential equations. Alright, before we get to solving separable differential equations, we need to first understand what a differential equation is. And basically, a differential equation is any equation that uses the derivative. So a very simple differential equation would be like dy dx is equal to x. If we wanted to make it more complicated, you could say dy dx is equal to x plus 1 over x. But it needn't be restricted to just having the x terms in it and the dy dx terms in it. For example, we could include the original function in it. So dy dx equals y over x squared plus 1 would be a differential equation. Or you could say x dy dx is equal to y plus x squared over y. So it doesn't matter whether you have x's or x's and y's, or you could even just have y's, but any equation that includes a derivative in it, differential. And if this derivative is the first derivative, as shown here, then it's called a first-order differential equation. Now, there are second-order differential equations. You might see something like y prime prime plus 5y prime is equal to x squared minus 3. This is a second-order differential equation because we've got the second derivative as well as the first derivative. In this video, and actually in our class, we are only going to focus on first-order differential equations. And with these equations, more importantly, we're going to focus on the kind that are separable. An equation that can be separated between, maybe on one side of the equation you have all x's and dx's, and on the other side of the equation you have all y's and dy's. If you wish to explore the world of non-separable differential equations, you can do that in a differential equations class, or if you want to see some on the side, I would be happy to brush up on my skills and share some with you outside of class. So let's get to it. In part 1, or example 1, we are asked to solve this differential equation, and they give us 3 initial conditions. So what we're going to see is that when we solve a differential equation, we get a general solution, and in going through that initial condition, we can find a particular solution. So here's where we start, and the first step, the very, very important step, is for us to isolate or separate the variables. So I move all of my y terms to the left-hand side of the equation and all of my x terms to the right side of the equation. From there, what I'm able to do is I'm able to integrate both sides. And if I integrate the left side, I get y to the third over 3, and then I'm going to write plus some unknown constant is equal to x to the third over 3 plus a different unknown constant. And these are kind of going to eventually collide together into a single unknown constant. If I multiply both sides by 3, what's going to happen is it gets rid of this denominator, and we'll get y to the third equals x to the third. And let's take all of our c's and put them together on one side and multiply it by 3. So this constant here is basically 3c1 and 3c2. We're mashing them together into some single unknown constant. And then finally we can conclude that y is equal to the third root of x cubed plus c. There is our general solution. we found a single equation. So there's our equation. That would satisfy the differential equation. We could actually plug this in to this and see if the derivative of this function is equal to that. But we'll save that exercise for future problems. And let's advance on to part A, B, and C. So in part A, they want us to use the initial condition of y of 0 is equal to 2. So what we can do is plug those values in, and we get the y coordinate is equal to the cube root of the x coordinate plus c. And in solving this problem, we see that c is equal to 8. And so we can draw our final equation up as y is the third root of x cubed plus 8. So if we were to take a look at our graph over here on the right, 0, 2 is probably that point there. We're pretty close to it. And the differential, or the particular solution, would go through that. Trying out a different initial condition, in part B, what we have is the y coordinate of -2 is going to be used with the x coordinate of 0. And in this case, we would find that c is equal to -8. So our equation in that particular initial value would be the cube root of x cubed minus 8. And looking at our graph, if we plot a point at 0 equals -2, our slope field would show us probably a curve that kind of resembles this one. So there's two solutions there. And finally, going on to part C, our initial condition is 0. So we say 0 is equal to the cube root of 0 cubed plus c, which indicates that c is 0. And we're able to draw the conclusion that y is equal to the third root of x cubed plus 0. Or very simply, y equals x. And that looks like that's drawn in with this solution. What we're seeing here is that with a different initial condition, we are provided with a very different looking function. These three curves may not even belong to the same family of functions. And that often happens with these separable differential equations. You get curves that don't belong to the same parent family. They're not transformations. So let's take a look at example 2. All right, in example 2, we are going to start by separating the variables. So we have dy dx is equal to x squared y. And if I move my y to the left, 1 over y dy is equal to x squared dx. And then I'm going to integrate both sides to start to solve the problem. And we get the natural log of the absolute value of y is equal to x to the third over 3 plus c. And I went ahead and I combined the left-hand c into the right-hand c. And now I want to start solving this for y. So the first thing I'm going to do is I'm going to exponentiate both sides. X cubed over 3 plus c. And this plus c can actually come down so that what I have is e to the x cubed over 3 times e to the c. And e to the c could be treated as a whole new constant, so that what I have is, I'll call it k, or I could have called it c2. And we get this going on. And then to remove the absolute value, k could either be positive or negative, and that will be determined when we have an initial condition. So let's just go y is equal to, we'll call the constant now a. And in truth, we could have left with a c every single time, but I wanted to really distinguish the difference between this constant right here, this c, with the whole thing being a constant versus the positive or negative version of that for the absolute value. So now we have our general equation. If we plug in our initial condition that's described in part A, what we get is 1 is equal to a e to the x cubed over 3. Whoops, and that x happens to be a 0 in this case, so we'll write that in as a 0. And what we find is a is equal to 1. So our equation would be y equals e to the x third over 3. There's our particular solution for the first initial value. Moving to the second initial value, we have a scenario where negative 2 is equal to ae to the 0 cubed over 3. And in this case, we see that a would wind up being negative 2. So our equation, the particular solution, would be y is negative 2e to the x cubed over 3. And there's our particular solution for the second case. Okay, when solving these differential equations, sometimes they want you just to find a general solution, and other times they actually give you the initial value, and we use that to find a particular solution. So please read the question carefully to determine whether you're finding a general or a particular solution. And remember, with a particular solution, you'll need an initial value. So sometimes you'll see these problems referred to as IVP, initial value problems. So let's look at example 3.
It feels good to be a gangster.
Okay, so sometimes we need to do some upfront manipulation before we start the separation of variables. And in this case, it's a pretty clean variation. We can take the e to the x and change that so that the e to the minus y moves to the denominator. And we used our exponent rules for that. And then we can separate our variables. E to the y dy is equal to e to the x dx. From there, we can go through the process of integrating both sides, and we wind up getting e to the y is equal to e to the x plus c, and then we take the log of both sides, and we get y is equal to ln of e to the x plus c. And there we have it. There's our initial value problem. We don't have an initial value, so we just get the general solution. And keep in mind this c is not up in the exponent, but is down below. Moving over to the right-hand problem, we can move the x to the right side, and we get dy dx is equal to x plus xy squared. And then trying to isolate that x out, what we can do is we can factor an x out and get 1 plus y squared. And now the variables are separable. So we move the y piece to the left-hand side, and we get 1 over 1 plus y squared dy is equal to x dx. And now that our variables are separated, we can integrate each side, and we find that the left side is the arctan of y, and the right side is x squared over 2 plus c. And then to isolate the y, we take the tangent of both sides. Y is equal to tangent of x squared over 2 plus c. So there's our general solution to the first order differential equation. All right, the last problem for today, example 4. What we have here is another differential equation. It looks like we might need to do some manipulation first. If we move the x to the right-hand side, what we'll have is y dy dx is equal to x, and then we can multiply the dx across, and we get y dy is equal to x dx. If we integrate both sides, we will wind up having y squared over 2 is equal to x squared over 2 plus c. And then I'm just going to get rid of that denominator by multiplying everything by 2. And what we have is y squared equals x squared plus c. And this is a general solution. Some people might take it a bit further and write this as y is equal to the square root of x squared plus c, which is fine, but you need to remember that if you're going to square root it, you have a plus and minus to account for. So I'm going to leave it in this format because it makes it easier in my eyes to do part B. Part B, we're using initial conditions to find particular solutions. So with the initial condition of 0, 4, what our equation looks like is y squared equals x squared plus c. We plug in those values into the initial condition and we get 16 is equal to 0 plus c. And we very quickly find what our c value is. So we can write y squared equals x squared plus 16. If we needed to go all the way to the point of solving exactly for y, which is a good habit when we're actually finding the particular solution, we can write it as such, and we know that it's going to be the positive square root as opposed to the negative one because we have a positive y value. If we had a negative y value, then we'd want the negative square root. Okay, part II, we're given the initial condition of negative 4, 0. So if we plug that in, we'll have 0 squared equals negative 4 squared plus c, and we see that our c value is negative 16, and we have the equation y squared is equal to x squared minus 16. And then finally in part 3, the initial value is 0, 0. So what we get is 0 equals 0 plus c, and or 0 squared equals 0 squared plus c. And we find that c is 0, so our equation would be y squared equals x squared, or very simply, y is equal to x. Okay, so today we worked at solving some separable differential equations. Tomorrow we are going to extend that to separable differential equations that commonly get used in modeling problems, generally laws, exponent laws where you have population growth or decay. And we'll get more practice with that tomorrow's video. Have a good evening.